Hi everyone. So I'm glad to be here. So today I will do some introduction about the TVM compiler stack and how we can support ONNX by TVM. So I think a lot of people know TVM, but I want to do some brief introduction here as well. So originally, TVM referred to the Tensor IR stack, and ONNVM is a graph IR stack. But recently, the ONNVM repository in the GitHub has been merged into the TVM repository. So TVM refers to a complete deep learning stack from the graph level down to the tensor level now, I think. So TVM is a community project led by Tianqi Chen from University of Washington. And there are a lot of contributions from companies like Amazon, Huawei, NTT Lab, DeepMind, and a bunch of universities and organizations like University of Washington, Shanghai Jiao Tong University, Berkeley University, Hong Kong, UST, and some other organizations like Apache. Yeah. So MXNet version 0.9 fully adopted ONNVM TVM framework. So and we can see how it is used in MXNet, right? In the MXNet source tree. As a community project, TVM is well received by the community. We can see that there are already around 2,000 stars in the GitHub, and a lot of contributors, around 130. Maybe the data is a little old because I prepared the slide maybe 1 week ago, so it should be more. Okay, so this diagram is about the TVM architecture. So for deep learning, we need to support different kinds of hardwares, different heterogeneous accelerators. Here, you can see that TVM can support now a lot of hardwares, CPU, GPU, FPGA, and there is some plan to enable ASIC support, and there is a simulator for verify your hardware design. So it is very cool design called the VTA accelerator, open accelerator stack, which I will have a page for introduction about this part. So from OS part, so you can use Windows, Linux, Mac OS for the host OS for the TVM development. And for deployment, we can support Android, iOS, and Linux, right? So moving up, this is what we support in TVM, right? From up level, we support various front ends, MXNet, right? ONNX, Keras, AutoML, TensorFlow, and the last one is darknet, which is recently added as a front end of the TVM graph support. So move down. So there is a graph IR called ONNVM. So ONNVM is a computational graph IR implementation. So and then a bunch of graph optimization can be done in the graph level, just as Tom just mentioned before. Yeah. So for example, you can do some memory plan, you can do some operator fusion, you can do some data layout transformation. And then the graph, after the graph optimization, you can do some tensor level or operator level optimization and scheduling, right? So there is a tensor expression language defined in TVM implementation, which is based on the Hardy IR, which is also a very popular framework for image processing. So, and here we have a definition about schedule. Schedule is some transformations about the computation. So a lot of schedule primitives is defined in TVM, and we can do optimizations in the schedule level, right? For example, the loop transformations, the thread bindings, the cache locality, and specific for GPU acceleration, there is thread cooperation, tensorization, and such kind of a schedule primitive support. So, and another new feature added recently to the stack is AutoTVM. I think Tom also mentioned it a bit just before. Okay, here I want to talk a little bit about the deployment mechanism supported by TVM. It is RPC, remote deployment mechanism. So you can compile the model on your host device, or even in the cloud side, right? So just you need just the network access to access the target device. And in device side, there is a runtime, right? You just run the output of the compile process. We can see on the left that the demo Python code, right? We imported the ONNX model, right, which is trained already from different frameworks, right? So we import a framework and transform it to the NNVM graph and call the NNVM compiler build to generate the execution level graph and the library. The library actually is some TVM modules. TVM modules, it contains some packed functions for calling in the runtime side on the target device. So for the execution graph, it is in JSON format, right? So here I just a small diagram here for the JSON specification. So nodes, import arguments, outputs are defined, right? So in the node definition, there should be operate, import, attributes, such kind of things. So on the target device, with output from the TVM compiler process, we can create a graph runtime from the execution graph, the libraries, and different contexts. This context can be specific for different hardware. For example, a CPU context, right, with an LLVM. It can be an OpenCL context using the Mali GPU. It can be an FPGA context using PinQ hardware, right? So yeah, and then you can set import to specify the imports to the runtime and call the run function to execute the prediction with the new data you get on the device side. So I think the TVM runtime is good at that to reduce some binary size, right, and reduce some runtime overhead for the graph model conversion, such kind of things, right? I think it is very critical for devices with limited resources. Okay, so here I will do some introduction about AutoTVM, which is an automated optimizations. Normally, in the deep learning world, we are using handed optimization, right? So, but it requires a lot of effort, right? You need to do a lot of experiments to find the best results. So the TVM community introduced the automatic way to do the optimizations, which can reduce a lot of tedious work for developers, right? So machine learning-based framework is designed to do the automated optimization with domain-specific cost model. So, and transfer learning can be used to accelerate optimizations for great workloads with a lot of tensor operators. So to do the automated optimization, there are major two steps. One step is define a search space, right? And then you can run a search algorithm to explore the space to find the best config. Currently, 4 kinds of tuners are supported already in TVM. One is a random tuner in random order, right? Grid search in grid search order, right? GA tuner, which is a genetic algorithm using. Okay, and the most advanced one here, or with best performance in these tuners, I think it is XGB tuner, which is extreme gradient boosting algorithm. So I think this is also an open source project from Tianqi, I think, if I remember correctly. And with this automated optimization mechanism, or existing hand optimization can be part of the search space. So your previous work still can be leveraged to make sure that the optimization effort can be still used. Here is some data from the TVM community, right? So there is a paper called, the title is Learning to Optimize Tensor Programs. If you have interest, you can read the paper, right? So on the left, it is some comparison between TensorFlow Lite and AutoTVM. We can see that there is a great speed up for the performance. And on the right, there is some comparison between ARM Computer Library and AutoTVM. Here, version 18.3 is used for ARM Computer Library. And I think with recent versions of the ARM Computer Library, they should have better performance. But this is just for some comparison. So we can also see that AutoTVM can provide some performance gain as using computer library as a baseline. Okay, so this is the VTA Open Accelerator stack. I think it is very helpful for people doing a hardware design, right? If they want to design some deep learning accelerator. So for the VTA Open Accelerator stack, it is integrated with the TVM stack very well. So there are major three parts. One part is the VTA JIT runtime, right? The up-level schedule can call the JIT runtime to do the computation, right? Another thing is the VTA ISA. It defines several instructions to do the deep learning acceleration, right? So we can see that the VTA microarchitecture, there are some instruction fetch operation, memory load, and memory store. And on the core of the diagram, you can see that there is a compute module which supports ALU operations and GEM operations, right? So, and after the microarchitecture, we can deploy it on the edge FPGA. For example, the PinQ FPGA from Xilinx is supported now. And there's some plan to deploy it to the cloud FPGA instances from Amazon. And we can also deploy it to the simulator. Okay, the whole process is that we can use TVM to do schedule optimization and deploy it remotely via RPC. And on the target device, the RPC server can call into the JIT runtime and deploy the VTA stream onto the FPGA device. I think it is very helpful to verify some hardware design and to do some early verification. And there is also one paper from the TVM community. If you have interest, you can also read about it. So here, we can see on the GitHub the TVM Public Roadmap. So, for example, there is some plan to enable 8-bit support and even some lower bit precision support, 4-bit, even 1-bit. And there is also some plan to enable graph-level AutoTVM, or automated tuning. So currently, AutoTVM is just for tensor level. So if you want to do it in a graph level, right? So there is also some plan in this part. For VTA, there is some plan to enable the Ultra 96, which is an FPGA 96 board from Xilinx with a Xilinx XenQ SoC. And there is some plan to enable Amazon F1 instance, just as mentioned. So for another important part for next release is the high-level IR improvements. Previously, we have NNVM. So NNVM v2 is in the plan. It is called a relay. So there is some discussions about it. So because with the industry evolvement, we need to support control flows, right? And improve the type systems, right? How to make the control, make the runtime and the compile subsystem work together better. This is also one important consideration about this new relay design. Yeah. Okay, for ONNX, I think it is also mentioned a lot in the previous session, so I will just go through it quickly. So ONNX defines actually three major parts. One part is the computation graph model. Another thing is the built-in operators and some standard database. But it is only for neural network. For ONNX ML, it is a classical machine learning extension, not necessarily open neural networks. So how to support ONNX models in TVM, right? ONNX model defines the graph, defines the nodes. We needed to import it and do some offline conversion to the NNVM symbolic graph. So there is an ONNX front end implemented in TVM to support ONNX model. So I think there are some angles or factors we need to think about to support ONNX model in TVM. I think one level is the operator level, right? ONNX already support defined a lot of operators. So TVM, there is also some definition or implementation. So we probably need to think about the operator definitions. What operators are supported in ONNX? What are supported by TVM? So shall we support all the operators defined by ONNX in TVM? This is a question to investigate. And another thing is model, the accuracy and efficiency for the model conversion, right? Because some people told me that they ran into a lot of problems before for converted ONNX model to NNVM graph. So this is probably another thing we needed to check, right? Yeah, so because the offline conversion, right, there is some maybe mismatch or some supported missed. So yeah. And we can also think about the graph level optimization. So for ONNX, there is ONNX optimized, defined or implemented for some common level optimizations. And in TVM side, there is also some graph level optimization implemented in NNVM. So we can probably think about how these graph level optimizations can be handled. Shall we merge it? Or we still should have some pass-through method to just use the TVM graph optimization directory. So somebody may ask, why not use ONNX directory as a graph IR in TVM, right? Because they are quite similar, right? So just they are both computational graph IR, right? So yeah, it's a good question, I think. So there is also some discussion in the community about this. It looks like there is still some limitations of ONNX for a TVM. So they still want to use a relay at this moment. So I think this is one thing we probably, the ONNX community and the TVM community can work together, right? For the merging in the future, I think. Otherwise, we still needed to do the graph model conversion, right? It is not so efficient, I think, because it will require some overhead at runtime, right? So yeah, I think this is one direction we can probably think about. Okay, another thing I want to introduce is ONNXIFI. So ONNXIFI is an ONNX interface for framework integration, which is released in latest ONNX version. Should be version 1.0, I think. So ONNXIFI is a standard interface for neural network inference on different accelerators. So it supports runtime discovery and selection of execution backends. And for each backend, we can also do some runtime discovery of ONNX operators. And it can support ONNX model format and online model conversion. For ONNX backend, it is a combination of software layer and hardware device to run an ONNX graph. So the same software layer can expose multiple backends. For example, CPU backend, GPU backend, DSP backend. And there is also one heterogeneous type of backend defined, because maybe the backend wants to handle the scheduling or dispatching to different devices by itself, right? So in this case, you can use the heterogeneous type so that you can do your own CPU platform level optimization, including CPU, GPU, DSP, and maybe NPU. So with ONNXIFI, three categories of API are defined. One category is for the backend, right? Get a backend ID, get a backend information, right? To do the initialization, such kind of things. Another thing is event. Event is used to do the synchronization. And another category is the graph, right? We need to init the graph, right? Set the graph I/O and run the graph. Okay, so this is a diagram I just draw for discussion. I think currently there is one global backend implemented by Facebook already for ONNXIFI. I think it can be used as a good reference how we can support ONNXIFI and integrate with the up-level applications and the up-level frameworks, right? So here, for other backends, I think it should be still open for discussion how we can support ONNXIFI, right? Probably we can add a TVM backend using libONNXIFI TVM library. We can add a snappy backend. We can add an ONN backend. We can add a Tensor Arch backend. I think it should be part of the future work. And the community should think about how we can support it better to make it a unified standard interface for all the ecosystem. I think we, as an ecosystem, this is a very important thing to consider, because each vendor may have their own specific requirements, or they have some specific implementation. And how to fit into this diagram, I think it is a topic we can discuss. So specifically for TVM, right? So TVM and for TVM RPC Deploy, right? So we do the AOT ahead of time compilation, right? So how the compile and the runtime mechanism can be supported, right? So in this mechanism, right? So I think this is, I still have no good idea about this part yet. So if somebody have idea about this, welcome for discussion. Okay, I think that's all. Thanks everybody.
Any question for Jami?
In the AutoTVM slide, you mentioned that you could incorporate one of the hand-coded implementations as part of the search space. Mm-hmm. What's the representation for that hand-coded implementation?
Oh, okay. For example, if you want to do the tiling, right, and you already have a hand optimization with, for example, 4 multiply 8, right? Mm-hmm. So you can specify, add it to the list of a search space, right? For the search space.
Okay, so yeah. That's still represented in TVM?
Yes, okay. Yes. Currently, yes.
So I'll ask a question. So ONNX, initially we understood that ONNX is a description format, and ONNXIFI is rather a runtime API. So does it mean that ONNX is creating two different sub-projects?
Yeah, from my understanding, it is yes. So the ONNX ecosystem is expanding, not just the open exchange format, right? So because there are still some, not just the model format, right? We still need to unify the API, right? So that the up-level applications can call the single standard APIs to do the runtime inference. I think this is this will also be very helpful for the developers in this area. Yeah.
Thank you very much. Any other question for Jami? Okay, then I think we can pause for lunch, and we will restart at 2.
Yeah.
Thank you, Jami.
Thank you.